Star formation is a fascinating and complex process that takes place in the cold, dense regions of molecular clouds, where gas, dust, and gravity play critical roles. These fundamental components serve as the building blocks for new stars, and understanding their interaction is essential to grasping the broader mechanisms at work in the universe. This essay explores the key ingredients for star formation: gas, dust, and gravity, examining how they contribute to the birth of stars and the factors influencing their formation. Gas is the most abundant ingredient in the universe, and it plays a central role in the formation of stars. The majority of the gas in molecular clouds is made up of hydrogen, the simplest and most abundant element in the cosmos. In these clouds, hydrogen exists primarily in the form of molecular hydrogen, H2, which is highly effective in cooling the gas, allowing it to condense and form dense regions where stars can form. The coldness of molecular clouds, typically around 10 to 20 Kelvin, encourages the formation of molecules, which in turn help to trap heat and further cool the gas, facilitating the compression needed for star formation. The gas in molecular clouds is not uniform, but instead exists in clumps and filaments, with varying densities. Some of these regions may be dense enough to become gravitationally unstable and begin collapsing under their own weight. However, the process of gas collapse is not straightforward. It requires the gas to lose energy in the form of radiation so that it can continue contracting. If the gas remains too warm, thermal pressure will counteract gravity and prevent collapse. This is where dust plays a crucial supporting role, as it helps the gas cool down by absorbing and re-emitting energy. Dust is the second key ingredient in the star formation process, though it makes up only a small fraction of the mass in molecular clouds. Despite its relative scarcity, dust is essential for cooling the gas and enabling star formation. Dust grains, composed mainly of silicate and carbonaceous material, act as effective heat sinks. When gas molecules collide with dust particles, they transfer energy to the dust, which then radiates it away in the form of infrared radiation. This cooling process allows the gas to contract further under the influence of gravity. The presence of dust also affects the dynamics of the gas. Dust grains can enhance the ability of gas to cool by providing a surface on which molecules can form. For instance, dust serves as a catalyst for the formation of molecular hydrogen, the dominant form of hydrogen in star-forming regions. Without dust, the rate of molecular hydrogen formation would be much slower, hindering the cooling process and potentially stalling the collapse of the gas. Moreover, dust plays a significant role in the overall structure of molecular clouds. The intricate interplay of dust and gas creates complex structures like filaments and cores, which are crucial for the formation of stars. These dense cores, often referred to as stellar nurseries, are where individual stars or groups of stars are born. The dust, in combination with gas, forms the backbone of these structures, helping them to maintain their stability while allowing for the gradual buildup of material that will eventually become a star. Gravity is the third and most essential ingredient in star formation. While gas provides the raw material and dust facilitates cooling, it is gravity that drives the collapse of the gas and dust into dense regions, ultimately leading to the birth of stars. Gravity is a fundamental force that acts on all matter, and in star-forming regions, it pulls the gas and dust particles together, causing them to collapse under their own weight. The initial stages of star formation often begin in regions of a molecular cloud where the gas is slightly denser than its surroundings. These over-dense regions experience a stronger gravitational pull, which causes them to collapse. As the gas particles move closer together, they collide with increasing frequency, which leads to the release of gravitational potential energy in the form of heat. This heat raises the temperature of the collapsing region, causing it to shine as a protostar. However, the collapse of the gas is not a simple, uniform process. As the gas condenses, it begins to fragment into smaller clumps, each of which may eventually form its own star. These fragments are known as stellar embryos, and they represent the earliest stages of star formation. The dynamics of this fragmentation are influenced by factors such as turbulence, magnetic fields, and the feedback from other stars in the region. gravity also plays a key role in determining the mass of the star that forms. The more massive a molecular cloud, the greater the gravitational pull it exerts, leading to a more rapid collapse and the formation of a more massive star. However, there are limits to how much mass a cloud can accumulate before its self-gravity becomes unstable. This is why most stars form with masses comparable to the Sun, though there are exceptions, such as massive stars that form in the densest regions of molecular clouds. While gas, dust, and gravity each play distinct roles in star formation, their interactions are what truly drive the process. The gas provides the material, dust helps to cool and condense the gas, and gravity pulls it all together to form stars. These ingredients are not isolated, rather they work together in a delicate balance. If one factor is altered, it can have profound effects on the overall process. For example, the presence of dust can significantly affect the temperature and density of the gas. In regions of molecular clouds where the gas is colder, gravity is able to overcome the thermal pressure, allowing for the collapse of the gas into dense cores. However, if the gas is too warm, it may not collapse efficiently, and star formation may be delayed or inhibited. In some cases, the cloud may be prevented from collapsing altogether by external forces, such as the pressure from nearby supernova explosions or strong radiation fields from massive stars. Gravity also plays a role in the distribution of gas and dust within molecular clouds. The process of star formation is often not uniform, and different regions of the cloud may collapse at different rates. This results in the formation of a wide variety of stellar systems, from single stars to binary systems, and even large clusters of stars. The final configuration of stars depends on the initial conditions of the cloud, including its mass, temperature, and the amount of turbulence and magnetic fields present. The cooling of the gas through dust is also influenced by the density and structure of the cloud. In highly turbulent clouds, the gas may not collapse in a smooth, uniform manner. Instead, it may fragment into smaller clumps, each of which may go on to form individual stars. In such cases, the formation of multiple stars from a single molecular cloud is common, leading to the creation of star clusters. Star formation is a highly intricate process that depends on the interplay of gas, dust, and gravity. Each of these ingredients contributes to the overall dynamics of the process, and their interaction determines the characteristics of the stars that eventually form. Gas provides the raw material for star formation, dust facilitates cooling and enhances the collapse of the gas, and gravity is the driving force behind the condensation of material into dense regions that will eventually form stars. The balance between these factors is crucial to the process, and even small changes in one ingredient can have a profound effect on the outcome. As we continue to study star formation, new observations and simulations are providing deeper insights into the complexities of this process. Understanding the roles of gas, dust, and gravity not only helps to illuminate how stars are born, but also offers clues about the evolution of galaxies and the broader structure of the universe. Through continued research and exploration, we will gain a greater appreciation for the intricate and beautiful process that creates the stars we see in the night sky.